Hello, welcome back to Math 155. Today we're going to be talking about nonlinear systems of ordinary differential equations. One really famous example of a nonlinear system is an interaction between lynx, the predator, and hares, which are its prey. And if we look at data going back into the 19th century, we see these cyclical dynamics where the number of hares increases and that allows the lynx population to expand. But then that causes the number of hares to decrease because they're predated on by the lynx. And then when there's not enough food to go around, the lynx population decreases, and then this cycle can repeat. So we want to look at models that can capture these sorts of dynamics. So we'll be talking again about nullclines, about equilibria, and in particular something new called the Jacobian, and a particular type of predator-prey model called the Lotka-Volterra model. So if we want to talk about predator-prey populations, we want to think about interactions between our predator and prey. So the predator have to catch our prey, and the amount of prey that they're going to catch is going to depend on the efficiency with which they're able to catch those prey, as well as the number of prey that is around and the number of predators that are around. So we want to write down some nonlinear differential equations. So if we have our general system, which is a 2D autonomous system, dx dt is equal to f of x, y, so f is just some function of x and y, and dy dt is some function g of x of y, then we can write down a particular type of predator-prey model, which is called a Lotka-Volterra model, where dx dt is equal to rx minus axy, and dy dt is equal to minus ky plus bxy. What's going on here is if we imagine, first of all, a case where there's no prey, then in that case, there's no prey, this term goes to 0, and our predator equation just decays towards 0. So there's no food, so no prey implies no food. So y just turn towards 0, so the predator will die out. And if we think about what happens if there's no, if there are no predators around, then this term goes to 0 in our prey equation, and we end up seeing just exponential growth for our prey. So this is our prey equation here, and this is our predator equation here. So we can think about what happens in the absence of either the prey or the predator to the other species. We end up seeing that the prey would grow exponentially and the predators would decay exponentially. But when we have them there together, we have these terms a, xy, and bxy. And these terms here, they tell us about the interaction between the predator and the prey. So a and b are both positive constants, and so this minus axy is telling us that the predator is decreasing the prey population by eating them, and the plus bxy is telling us that the when the predators feed on prey, they're able to convert that to biomass, and they're able to produce new offspring, so that population is able to grow. Okay, so let's look at a specific case of this model. So we're just going to plug in some numbers here for our different parameters. And what we're going to do is we're going to draw phase planes to understand what's going on. So the phase plane will tell us about the qualitative behavior of our solutions. So we just want to essentially have an informed sketch of what's going on. So we're going to find our nullclines. And before, when we were looking at our linear systems, these were just straight lines. We only had one nullcline for our dx dt equation and one for our dy dt equation. Now we can have multiple nullclines because we have these nonlinear systems. So we have a nonlinear equation to solve. We're going to find our equilibria in the same way as we had before. So our equilibria satisfy dx dt is equal to 0 and dy dt is equal to 0 simultaneously. And we're going to examine the stability of our fixed points. So we can sometimes do this graphically, but we using our sketch, sometimes we might want to do this algebraically as well. We'll talk about that a bit later on. And then we can also, if we've got our phase plane, we can sketch on some direction vectors and trajectories, just like we did with our linear systems. So just to recap, our nullclines are just where our dx dt or our dy dt equation is equal to 0. So if we have x on our horizontal axis, then that means that we are moving up or down in this case. And if our y is on our vertical axis, then we are moving left or right on our dy dt is equal to 0 nullcline. So in our particular case of our block of Volterra model that we've got above, the specific one we've got shown at the top of this slide here, 24.2. Wow, what are our nullclines here? So dxdt is equal to a half of x minus 2xy. We want to set this equal to 0. So we can rearrange that and we get x by half minus 2y. So x is either equal to 0, this must equal to 0. So x is equal to 0 or y must equal a quarter. On y nullclines, we've got dy dt is equal to minus y plus xy equal to 0. This tells us that y divided by minus 1 plus x is equal to 0. So either y is going to be equal to 0 or x is equal to 1. So here we've got 4 different nullclines. They all happen to be straight lines, which makes it nice and simple. But previously in our linear systems, we'd only ever have 2 nullclines. So now when we're thinking of these nonlinear systems, we need to account for more than 2 nullclines. So let's sketch what this looks like. So we've got x and y here. I'll talk about the direction field in a moment. Okay, so what's our first nullcline? Let's do the ones for dx dt first of all. So we've got x is equal to 0. So that's this nullcline here. And we've also got one for dy dt when y is equal to 0. So let's draw that one on as well because it's nice and simple. And then our other nullcline, our x nullcline, a nullcline is sometimes called a zero isocline as well, but we'll always refer to them as nullclines in these questions. So the other one is y is equal to 4. So y is equal to 4. We're going to have another blue line. So let's put this here. It's nice and straight horizontal lines or vertical lines, which is nice and easy. And then we've got a y nullcline at x is equal to 1. So let's put that here in the right color. Okay, so first of all, where are the equilibria? Well, they're going to be at the intersection of the blue and red lines. So there are 2 in this case. Let's think about what's going on in the flow in this system. Well, if we think about, first of all, on our x nullcline, so think about on the line x is equal to 0. Well, on the line x is equal to 0, we're going to have dy dt, if we go all the way back to our equations up here, when x is equal to 0, this is going to be equal to 0. So dy dt is just going to equal minus y. So that means that on this blue nullcline here on the left-hand side, we have dy dt is equal to minus y. So our arrows are going to be going down. So let's just make sure we've got a key here. So these nullclines I'm going to be doing in blue, and these ones here in red. Okay, so that's what's going on the y-axis. So when y is equal to 0, we have dy dt is equal to 0, so we're on a y nullcline. And if we go back to our dx dt equation, when y is equal to 0, this is equal to 0, and the sign of dx dt is the same as x. So that means that our arrows, in this case, going in this direction. Okay, what about on our other nullclines? Well, if we think about our y is equal to a quarter nullcline, again, let's think about what's going on with our dy dt equation. When y is equal to a quarter, then we're going to have minus a quarter plus x times over 4. So we can take out a factor of a quarter at the front. We're going to have minus 1 plus x. So the sign of this depends on x. So if x is greater than 1, then dy dt is going to be positive. And if x is less than 1, then dy dt is going to be negative. So let's go back down to our phase plane. We have this line here. It's going to be the line x is equal to 1. It's the line y is equal to a quarter. We've got 0 here. So on the right-hand side of this line, we've got, on this blue nullcline, our arrow is going to be going up because dy dt is positive. and on the left-hand side, x is less than 1, so dy dt is going to be negative. We can do a similar thing for our final nullcline here. So this is the nullcline when x is equal to 1. So on x is equal to 1, dy dt is equal to 0. Let's go back up to our equations here. So when x is equal to 1, we're on our y nullcline. So here we're going to have a half, x is 1, half minus 2y. So this is going to be less than 0 whenever y is greater than a quarter, and is going to be greater than 0 whenever y is less than a quarter. So that means if we go down to our phase plane again, when we're below this horizontal blue line, we're going to be going to the right because our dx dt is going to be positive. Above it, we're going to be going to the left because our dx dt is negative. You can think about what's going on in these regions as well by drawing on some additional arrows. So this tells us that we are going around in some kind of spiral, but we don't know whether we're spiraling in or we're spiraling out, or whether we're just going around in a center. So we need to do a little bit of algebraic analysis to understand exactly what is going on at the equilibrium. So first of all, let's calculate what the equilibrium is. So an equilibrium, recall, is going to just be a pair of values x star, y star, where we have both of our equations, dx dt and dy dt, both simultaneously equal to 0. So if we go back to our phase plane, we see this is the intersection of the blue and the red lines. So we've already worked this out. We've got a point here, 0, 0, as being one equilibrium, and another point is going to be 1 quarter. So the line x is equal to 1 intersecting with the line y is equal to a quarter. So we already know what our equilibria are. So if we just go back to our equation, dx dt is equal to 0, that implies that x is equal to 0 or y is equal to a quarter. So if you hadn't drawn your phase plane, you would have ended up with this. And then if x is equal to 0, our dy dt is going to equal to minus y, and that's only equal to 0 if y is equal to 0. So 0, 0 is an equilibrium. Similarly, if y is equal to a quarter, then dy dt is going to equal to a quarter of 1 minus x. And that's only equal to 0 when x is equal to 1. So 1 quarter is also an equilibrium. So like I said, you can either just read this off of your phase plane if you can. You're not always able to do that. You might need to work it out algebraically, just like I've done here. So if we think about these things graphically as well, these are just the intersections of our nullclines. So imagine that we've got, say, one nullcline that looks like this. These can obviously look like anything. And then we're going to have another nullcline that looks, say, something like this. Then we have equilibria at each of these intersections here. Okay, so they're both equal to 0 at these points. So that's an equilibrium, that's an equilibrium, that's an equilibrium, and that's an equilibrium. Suppose this was our dx dt, and this was our dy dt, both equal to 0. So when they're both, when we have intersections between these nullclines, then that means that they're both equal to 0, and so we have an equilibrium. So how do we work out the stability at an equilibrium? Well, in one dimension, we looked at the sign of our derivative at the equilibrium. So if we had dx dt is equal to f of x, we would work out f prime of x and set x equal to x star. And then if this was positive, then we had an unstable equilibrium. And if it was less than 0, we had a stable equilibrium. In two dimensions, we need to look at something called the Jacobian, which is a matrix. And this matrix is composed of the partial derivatives of f and g. So recall we've got a system dx dt is equal to fxy and dy dt equal to g of xy. So this Jacobian here is just the matrix of all the partial derivatives, and that matrix is evaluated at our equilibrium x star y star. So we have on the top row our partials with respect to f, and the bottom row are partials with respect to g, and in the left column these are taken with respect to x, and in the right column they're taken with respect to y. So this matrix here tells us about the stability at our equilibrium. So why is that the case? So where does this Jacobian come from, and why does it tell us about the stability? Essentially what we're doing here is something called linear stability analysis, and we're going to make a linear approximation, which we've done before for in other contexts. We're going to make it a linear approximation to the dynamics close to our fixed point, close to our equilibrium. So if, for example, we let u of t equal a small deviation from our equilibrium, so we're going to call that xt minus x star, and likewise I'm going to let b of t equal yt minus y star. So I'm going to move a tiny bit away from our equilibrium, and then if I want to work out the dynamics of u, so I work out du dt, well, this is just going to be dx dt minus dx star dt, and this is just equal to 0 because it's a constant. So this is going to be just f of x, y. And we can rewrite these equations here in terms of x and y, so that we end up with u's, v's, x stars, and y stars. So this is just equal to f of x star plus u and y star plus v. What we can do at this point is we can do something called a Taylor expansion. This is our linear approximation. So this is approximately equal to f of x star, y star, plus partial with respect to x, evaluated at our equilibrium x star, y star times by u, plus the partial with respect to y at x star, y star times v. Now, note again that this f of x star, y star is equal to 0 because that was just the right-hand side of our equation dx dt. And we know that when dx dt is equal to 0, by definition, we have an equilibrium, and we've called our equilibrium x star, y star. So that first term goes to 0. So you can say that du dt is approximately equal to our partial with respect to x, to x star, y star times by u, plus partial with respect to y, x star, y star times by v. And similarly, we can do the same for our y equations. So we end up with our dv dt now. It's going to be approximately equal to f of, sorry, not f, g. So recall our dy dt is equal to g of xy. So now we're going to just have g's instead of our x's. So we're going to have our partial with respect to g, evaluated at the equilibrium times by u, plus the partial with respect to y, our equilibrium times by v. Now at this point, hopefully you might realize that this looks a little bit like some things that we've looked at before in a slightly more complicated way. This is just a linear system. So if we let, I'm going to call it the vector x equal uv, and j equal f sub x at x star, y star, f sub y at x star, y star, g sub x star, y star, and g sub y at x star, y star. Then we can write dx dt is equal to jx. So this is a linear system where our matrix is given by this j, which was our Jacobian. So if we can work out the partial derivatives of our functions, f and g, then we can create this Jacobian. If we find our equilibrium, then we can substitute the equilibrium into this Jacobian. And then now we're just back into the case where we had a linear system. So what we're really doing here is we're saying, okay, we're taking a small perturbation away from an equilibrium, and then we want to see if that perturbation grows or decays. So if that small perturbation grows, then our equilibrium is going to be unstable. And if that perturbation decays, then it's going to be stable. So we can analyze our linear system, and that will tell us what's going on at in our nonlinear system at a particular equilibrium. Okay, so let's go back to our Lotka-Volterra equation. So in this case, our Jacobian is going to be, again, going to have our partial with respect to x, partial with respect to y of f, similarly for g, which in this case is going to be a half minus 2y minus 2x, y, and minus 1 plus x. And then we had two equilibria, if you recall, so we look at the stability of our linear approximation, our linear stability of the system at each of those equilibria. So at 0, 0, we just substitute these values in. We have j at 0, 0. It's going to equal a half minus 2 times 0, minus 2 times 0, 0, and minus 1 plus 0, which is going to be equal to a half 0, 0, minus 1. So that's our first Jacobian. And then at 1/4, our second equilibrium, our Jacobian in this case is going to be equal to 0, minus 2, quarter, and 0. So we've got our matrices, so we can use our trace and determinant conditions that we used before to look at the stability. So exactly the same as with our linear systems. Now all we're doing in our linear systems, we only have to look at stability at one equilibrium, which is the origin. But now we need to do exactly the same, but for each of our equilibria, and we use our Jacobian as our matrix. So if we work out our trace, so at 0, 0, our trace, which I'll call tau, is going to be equal to a half minus 1, so it's going to be minus a half, so it's negative. And our determinant, which I'll call delta, is going to be minus a half. So this tells me this is a saddle. So we had a negative determinant here. And then at 1/4, we're going to have our trace, tau is going to be equal to 0, and then our determinant is going to be equal to half. So this is positive. So in this case, we have a center. Okay, so now we can go back to our phase plane, which was all the way up here. Because we've got a center, this non-trivial equilibrium, we know that any point that we start at, we're not going to be spiraling or spiraling out, we're just going to be looping around. But the amplitude of those cycles depends on where we start. So we start at these different initial conditions, we get a different amplitude for these oscillations. We also have this saddle. We know that this is a saddle as well because if we can see it from this phase plane, that we can tend towards 0 along this y-axis, but we'll move away like this. So we can tend towards 0 if we are actually on the y-axis, x is equal to 0, but if not, then we're going to move towards it and then move away. So we end up with these, in this case, these big cycles that go off here and eventually come back down again. Okay, thanks very much.